Very good morning to everyone. So far, we are just complete our topics, that is what is benzene, what is aromatic compound, what is Hakel rule, and what are the difference between aromatic, anti-aromatic, and non-aromatic compound. That's all. So those students missed my previous classes. You can see my all lectures in my Google Classroom. Now let's start our today's class. So today we are going to learn more about benzene and its derivative. So as we know that benzene is an aromatic compound, and these aromatic compounds are also termed as arene in short form. These aromatic compounds also called as arene in short form. So these arenes are nothing but an aromatic compound. Whenever a hydrogen atom is removed from these arenes, so it's forming a aromatic group, like a functional group. So whenever a hydrogen molecule is removed from this arene, it's forming a aromatic group like a functional group. So this functional group, that is aromatic group, represent as R symbol. This R symbol. So its R symbol is coming from aromatic compound, because it's an aromatic compound. So aromatic compounds called as arene also, and from this arenes, if hydrogen molecule just remove from that, so it's become a functional group. So this group is referred as this symbol, that is R, AR. Now this benzene structure is a cyclic structure. This benzene structure is a cyclic structure. We all know that. But do you know who is first developing this benzene structure? So it is first developed by one German scientist, Kekule, around 1872. So here is Kekule's structure. Here you can see the all atoms, and here also Kekule's structure, where just line angle formula, just hiding the atoms, nothing else, other difference. So both of these are Kekule's structure. Okay, so this one is 1 and this one is 2. Now we all know the molecular formula of benzene, that is C₅H₉. It has 3 pi bond and total 6 pi electrons. So we have already studied all this, and we have also know that benzene has 2 resonance structure. Benzene has 2 resonance structure. So this one is the first structure and this one is the second structure. So both of these are the resonance structure of benzene. And this one in the right hand side, you can see this one is the hybrid structure. This one is the hybrid structure of benzene. It's nothing but the combination of structure 1 and structure 2. So this hybrid structure is due to the resonance, because it has delocalized pi electron. Now some textbooks draw benzene as a hexagon with an inner circle. This type of diagram you can see in some textbooks. Both of these are correct. Both of these, this one also correct and this one is also correct. But one thing we have to know, that who is the first develop this resonance structure of benzene? Can anyone told me? So it's a Linus Pauling in 1930 century who developed this resonance structure of benzene. In benzene, the actual bond length is 1.39 Armstrong for single bond as well as double bond. The actual bond length is around 1.39 Armstrong in both cases, single bond also for double bond, because it's a closed ring, or you can say it's a cyclic structure. So that's why both the length as well as single bond and in case of double bond, both are on an average it will be 1.39 Armstrong. But intermediate between carbon carbon single bond, intermediate between carbon carbon single bond, the bond length is 1.53 Armstrong, and for double bond, carbon carbon double bond, the bond length is 1.34 Armstrong. But whenever it is present in a cyclic ring or it's a closed ring, in case of benzene, it's become the bond length 1.39 Armstrong. Understood? Okay. Now, we all know that benzene is a planar molecule, but how it's look like in 3D or hybridization state, we just have to see it. So here it is our in left hand side, you can see that it's a stick and ball method in 3D model for benzene. So we all see that it will maintain the angle 120 degree for all sides. This will be this angle maintained for all sides, here also, all side having 120 degree angle. And this one is just our hybridization state. All you can see that carbons are all having p orbitals. So here is 6 carbon is there, here is 1 carbon, here is 2, here is 3. So like that all over it's a 6 carbon is there. So all carbons having p orbital, this is a p orbital, present in a p orbital, and it's maintain sp2 hybridization. So all carbons p orbital and sp2 hybridized, so it's present in a single plan. You can see that it's present in a single plan. Single plan. Okay. Now draw all possible resonance structure for biphenyl. As I told that benzene having two resonance structure, benzene having two resonance structure. So for biphenyl we having here two different cyclic ring. So for biphenyl we have to draw one by one for all the variants possible. So now we just have to draw the structure first and delocalize one by one the pi electrons. So we just have to delocalize this pi bonds. So here this one is moved to here, this one moved to here, and this one is moved to here, and this ring remain unchanged. So this one our first compound, this one is we are getting after delocalize the pi electrons, we are getting this compound. So after getting compound 2, we have to delocalize the second ring pi bonds, or you can say pi electrons. So like the previous one, we have just delocalized this pi bonds here, this one is here and this one is here. So after that we are getting the third component like this. So same thing we'll do it again, from 3 we getting finally the compound 4. So like this finally we have 4 different biphenyl resonance structure. Understood? Now, in case of two or more 6-member ring, in case of two or more 6-member ring with alternating double and single bond can be fused together to form polycyclic aromatic hydrocarbon. So here is your example, polycyclic aromatic hydrocarbon. So two or more 6-member ring alternating double and single bond can be fused together to form polycyclic aromatic hydrocarbons. So all are these polycyclic aromatic hydrocarbons. There are two different ways to join 3 rings together forming anthracene and phenanthrene. So as the number of fused ring increases, the number of resonance structure also increases. Like we have already seen that benzene, only one ring is there, so it's having 2 resonance structure. In previous slide we have seen that in biphenyl there are 2 rings is present. For that we are having 4 resonance structure. So as the number of fused ring increases, then the number of resonance structure also increases. So like example, naphthalene is a hybrid of 3 resonance structure, whereas benzene a hybrid of 2 resonance structure. So if we are taking the example of naphthalene, so this is the structure of naphthalene, like phenyl, biphenyl ring. So here we get 3 different resonance structure. Okay, so you have just delocalize these pi electrons one by one, and the second ring remain unchanged. We are getting the compound 2. Here also just moving the pi bonds one after another, and again we are getting finally the third components. So like this we can draw all the resonance structure of any aromatic compounds. Next, in case of heterocyclic compounds, we all know that it's carrying or it contain oxygen molecule, nitrogen molecule, and sulfur. So this oxygen, nitrogen, and sulfur, these atoms are called as heteroatoms. We must determine whether the lone pair. So in case of heteroatoms, they carries lone pair. So this will be a new thing. It carries a lone pair, which will also can delocalized, or it can participation in our conjugation process. So we have to see it one by one. So for example, aromatic heterocyclic compound like pyridine. In case of pyridine, you can see that here is heteroatoms is nitrogen. And it's also carrying one set of lone pair. But this lone pair is present, that's not meaning that it's always be part of your conjugation process. It will be depend its position. Okay, now you have to see that heteroatoms, whatever it's, maybe oxygen, nitrogen, or sulfur, whatever it is, so it will be attached to your pi bond directly. So you can see that here the nitrogen atom, that is the heteroatoms, directly attached to your pi bond. So that's mean it will already conjugation is there, so no need this lone pair to participate in your conjugation process. So it will remain outside your structure. So 2 resonance structure of pyridine is possible. Here is 1 and here is 2. Just delocalized one after another. So you can get the second resonance structure of pyridine, and its contain total number of 6 pi electron. Total number of 6 pi electron. Now if we are going for the 3D structure of pyridine, you can see that here is the nitrogen atom, and means the heteroatoms. So here the lone pair is the position is perpendicular to the plan of the total structure, and all atoms, means here is carbon is there, here is carbon is there, carbon is there, carbon is there, nitrogen is there. So all chiral atoms are in p orbital. They all are present in p orbital, and all are have maintained the sp2 hybridization. But the nitrogen atom directly attached for to the our pi bond. Here you can see the directly attached to the pi bond, or you can say the double bond. That's why this lone pair is no need for participation in the conjugation, so it will perpendicular to our axis. So that's why it will be come outside in your structure. Okay, next. So next example is we are taking that pyrrole. So it's also a heterocyclic compound. It's not only heterocyclic, it's a aromatic heterocyclic compound. Pyridine also, it's a aromatic heterocyclic compound. So it contains 5-member ring, 2 pi bonds are there, 1 nitrogen atom is there. So pyrrole also has p orbital, all the adjacent atoms, means carbon as well as the nitrogen. So complete the conjugation process, means it's maintain all the necessaries for become a aromatic compound. So you can see the structure of pyrrole. So here is the structure. You can see here only 2 pi bond is there, only 2 pi bond is there, but here is our heteroatoms is present. So this heteroatoms having also the lone pair with it. So lone pair in this case, means in case of pyrrole, this lone pair is needed to present in your conjugation, because you can see that the previous one, means in case of pyridine, the nitrogen having directly attached to the pi bond, or you can say directly attached to the double bond. But in this case, means in case of pyrrole, it's not having any type of double bond or pi bond directly attached with it. So that's why this lone pair is attached to the conjugation process. You can see in 3D structure, this lone pair is not perpendicular to the plan of this structure. It will be present in your p orbital. This will be present in your p orbital. You can see in a single straight line, it is present in your p orbital. So you just draw the line for better understanding. So this will be present in your same plan. So for that reason, in case of pyrrole, this lone pair is participation in your conjugation process. So it's also having total 6 pi electrons. So how get you getting the 6 pi electrons? Here is 2 pi bond is there. So 2 pi bond, that means you having 4 pi electrons, 4 pi electrons, and you getting here 2 lone pairs, means one set pair of lone pairs. So having 2 electrons, so 4 pi electron and 2 electrons you are getting from the lone pair. So total number of 6 pi electron is there. So it's also maintaining all the necessaries to become a aromatic compound. So it's another example of a aromatic heterocyclic compound. Okay, so this maintain all the criteria for becoming a aromatic compound. Okay, next, histamine. So this one is very important for your semester. This histamine is very important. So histamine is a biological active amine formed in many tissues. So you can get this compound in your body. So it is also a aromatic heterocyclic compound. It's also a aromatic heterocyclic compound. So you can easily understand that it's also maintain the all the criteria like pyridine and pyrrole, so become a aromatic compounds. So what are the compound structure like? You can see that the 3D structure of histamine. So here one interesting thing is that this structure having two different combination. One combination is from pyridine like structure. This it's having two nitrogen atom in the cyclic ring. It's having two nitrogen. Here is one, here is two. So this structure little bit similar to our pyridine. To remembering the structure of pyridine, okay, just wait, I give you the structure again. And also similar to the another atom, that is nitrogen atom, is the pyrrole. Here it is. So it's combination of two different structure, that is pyridine and pyrrole. So here it is our structure, that is pyridine and pyrrole. You can see this similarity. Here nitrogen is having carrying the double bond, or you can say pi bond is there, and pyrrole, there is nitrogen hydrogen molecule is there, and it will be not attached to your double bond, or you can say pi bond. And this lone pair is participation in your conjugation process. So here you can also draw this lone pair inside your structure. So this is all about histamine. So here you can see that the main difference, that is in 3D structure, you can see this lone pair is perpendicular to the outside of your ring, because this nitrogen is already attached. This nitrogen is already attached to your pi bond, or double bond, whatever you can say. And in case of this nitrogen, this lone pair is present in p orbital. So it is present in p orbital and in a same plan. So that's why this lone pair is participation in your conjugation process. It will present in your same plan, and all chiral atoms are maintain the sp2 hybridize. So this lone pairs from here, this lone pair is not present in p orbital, is perpendicular to the outside of the ring. But nitrogen, the atom nitrogen, is maintained the p orbital, and all are having sp2 hybridize. So you can see that this one means histamine also maintain all the criteria to become a aromatic compound. It's a cyclic compound. It's maintain the conjugation. Here double bond is there, single bond, then lone pair having the conjugation single bond, then again double bond, then again single bond. And cyclic compound is maintain the conjugation. It present in a planar. Okay. And also the total number of pi electron is, here is one pi bond, here is one pi bond, so four, total 4 pi electron is there, and plus one set of lone pair is there in conjugation. So from there you can get the 2 pi electrons. So total you are having 6 pi electrons. Okay, understood. So this histamine is very important. So for today's class, this is enough. Thank you everyone.